You're using it right now. In fact, you're probably never not using it, and yet you almost never see it. We're talking about the single largest, most complex, most valuable machine humanity has ever built, the U.S. electrical grid.
And that is not an exaggeration. It's an absolutely mind-boggling system. And to really get a feel for the sheer scale of this thing, you just have to look at the numbers.
So, let's start with capacity. The grid has about 1,000 gigawatts of installed generation. Now, what does that even mean? Well, try to picture 1,000 nuclear power plants all running at full tilt at the exact same time. That's the kind of power we're talking about.
And who runs this thing? It's not one giant company. No way. It's this incredible patchwork of over 3,200 different utilities all working together in this synchronized continent-spanning dance.
So how do you connect it all? With wires, right? We're talking over 160,000 miles of high-voltage transmission lines. That's enough wire to wrap around the entire planet more than 6 times. Just let that sink in. And the price tag? Just the transformers, these giant metal boxes that manage the voltage, they alone are worth an estimated $400 billion. This isn't just a machine, it's one of the nation's most critical assets. So, with all that in mind, where does all this electricity even come from? All right, let's start the journey where the electricity is actually born, the power plant. See, electricity isn't really a fuel, it's more like an energy carrier. It has to be made from something else, and here in the US, we use a pretty diverse mix of sources to do it. Okay, this is a really interesting snapshot of America's current energy diet. You can see natural gas is still king, making up about 43%. But look at this, wind and solar. Together, they're 22% now. That's a huge leap from where they were just a decade ago. Then you've got nuclear holding strong at 18%, and coal has dropped all the way down to about 10%. But how do you actually turn something like natural gas or coal into electricity? Well, for a lot of these sources, the basic idea is surprisingly simple. You're basically just running a giant super high-tech kettle. Seriously, you burn a fuel to create a ton of heat, which boils water into incredibly high-pressure steam. And that steam then just blasts through the blades of a turbine, spinning it like a pinwheel at thousands of rotations per minute to generate power. Okay, so we've made the electricity. Now what? How do you get it from a power plant in the middle of nowhere to a city that's hundreds of miles away without losing most of it? Well, you build an electrical superhighway. Here's the big problem you have to solve. Moving electricity through wires creates friction, or what engineers call resistive loss. And to get around that, you have to crank the voltage way, way up. Think of it like the water pressure in a fire hose. Higher pressure lets you shoot water farther with less effort. It's the exact same idea here, but instead of water, we're talking about voltages as high as 765,000 volts. And this whole voltage thing perfectly explains that historic war of the currents between AC and DC. Alternating current, or AC, won out because its voltage is super easy to step up for travel and then step down for safety using transformers. But here's the cool part. Direct current, DC, is making a comeback. It turns out to be way more efficient for moving huge amounts of power over really, really long distances. So today, we use special high-voltage DC lines as the grid's express lanes. All right, let's get to the final leg of this incredible journey. How does that super high-voltage power get from the highway all the way down into your home so you can charge your phone? This is where distribution comes in. This really lays out the whole trip. So power starts at the plant at a pretty manageable voltage, but for that long-haul journey on the superhighway, boom, it gets stepped way up to hundreds of thousands of volts. Then, as it gets closer and closer to your neighborhood, it has to be carefully stepped back down, bit by bit, for safe delivery. And that's the job of these things right here, substations. We have about 55,000 of them scattered all over the country. You should think of them as the interchanges and off-ramps of the electrical grid. They take that terrifyingly high voltage from the main transmission lines and start knocking it down in stages until it's safe enough for the power lines that run right down your street. So, we've made the power, we've moved it across the country, and we've delivered it to your house. It sounds pretty straightforward, right? Well, behind the scenes, the grid is performing this invisible, constant, and frankly astonishing balancing act that keeps the whole thing from falling apart. But when you have a machine this big, what is the single hardest, most critical part of keeping the lights on every single second of every single day? It all comes down to one thing: grid frequency. You can literally think of it as the grid's heartbeat.
Across the entire continental United States, every single generator, every motor, everything plugged in is synchronized to this perfect rhythm of exactly 60 cycles per second. That's 60 hertz. If that heartbeat flutters even a little bit, the whole system could collapse.
And here's why that's so incredibly difficult. You have to understand that electricity can't really be stored. You can't just make a bunch of it and stick it in a giant warehouse for later. It has to be used the exact instant it's produced. This means that at every moment, the amount of power being generated has to perfectly match the amount of power being used. If generation is even a tiny bit too high, the frequency rises. Too low, and it falls. It's a real-time balancing act on a knife's edge.
What's so amazing is that the grid basically has its own immune system to protect itself. It all happens in layers. In the first few seconds after something goes wrong, the massive spinning turbines in power plants across the country use their own inertia to automatically adjust. Then, over the next few minutes, automated computers send signals to other power plants telling them to ramp up or down. And finally, for bigger, longer-term adjustments, human operators step in to bring whole new power plants online. It's this constant, multi-layered defense system working 24/7.
And this brings us to the biggest question for our energy future. You see, the traditional power plants that provide a lot of that stability are slowly being replaced by wind and solar. And those are variable. They only work when the sun is out or the wind is blowing. So as we re-engineer this gigantic machine, the ultimate challenge is going to be, how do we maintain that perfect, instantaneous 60 hertz balance? Figuring that out is what will define the grid of tomorrow.